I'm Professor Ralph, and I welcome you to...
He knows a lot about chemistry. Professor Ralph explains.
Lesson, I'm going to talk about all the gases. So come on and watch my first experiment.
This experiment will be needing hot water, a bottle, and a balloon. In the water until it's hot. Then pour it inside the bottle. Be careful since the water is steaming hot. Then with the help of the other one, place the balloon over the bottle. Watch as the dead balloon rises to life. The increase in temperature in the environment of the balloon made the balloon inflate.
Wow! How did that happen? Why did the balloon expand?
Charles,
Oh, yes, teacher assistant. Since I put hot water on the container, the volume of the balloon also increases in size. Charles' law stated that absolute temperature and volume of a given mass of gas has a direct relationship when pressure was kept constant. This explains why as your temperature increases, the volume also increases. As the temperature decreases, the volume also decreases. Fun fact.
Yes. Well, you see, on June 5th, 1783, Joselle and CHEM used fire in order to inflate a spherical ball that is like 30 feet in diameter. And then it traveled high up in the sky for like 1.5 miles before returning back to Earth. Of course, this remarkable news spread throughout France, and coincidentally, of course, Jacques Charles heard of this news, and he replicated this using a balloon. And then the result of this experiment resulted to Charles.
Thank you. I hate history, but hey, did you know that Jacques Charles that the absolute temperature is temperature measured in Kelvin? That is why we need to use the Kelvin scale because 0 on the Kelvin scale corresponds to a complete stoppage of molecular motion. It can be represented by the formula V over T is equals to K.
Professor, please help me save my grades.
Don't worry, Professor will save you.
Let's go.
Let's go. Wait. Slow down. I'm tired. That gives me the question. I wonder how our lungs work every time we breathe.
Yes. Well, Professor, that is according to my research. Yes. Well, the Boyle's law can be applied every time we breathe. You see, the rib cage is not flexible and the thoracic cavity remains static. And at the tip of the rib cage, we have this thing we call the diaphragm, which separates the thoracic cavity from the abdominal cavity. And then, what does it say here? Yes. When the diaphragm relaxes, the muscle compresses upward. And then this decreases the volume capacity of the thoracic cavity, and the pressure in the compressed space creates a pump that forces the air outside the lungs every time we exhale. Like that. And then another thing I've researched is that, yes, Professor, every time we inhale, yes, the diaphragm contracts. It pulls downwards towards the abdominal cavity and expands the volume of the thoracic cavity. This decreases the pressure in the lungs and creates an empty space which forms a vacuum which sucks the air inside our lungs.
Boyle's law talks about the connection between pressure and volume, which was studied by a guy named Robert Boyle. He observed that volume and pressure are related to each other and that the product of these two determine the state of gas. When these two products are multiplied, it gives us a constant perfect for an ideal gas. So, did you guys get that?
So, does that mean that Boyle's law states that pressure is indirectly proportional to volume?
Yes, you are right. So, guys, did you get it better?
We have to hurry. Let's go. Oh, yes, let's go.
Professor, I want to impress my classmates with this magic trick I saw my brother was doing the other day. He was able to fit a whole egg inside his glass bottle when it couldn't even fit in the first place. I thought that would be cool to show to my classmates during the show and tell of our science class.
Fear not, because this needs a little touch of science magic. Let's use the Gay-Lussac's law.
Prepare the materials. You'll be needing a glass jar with an opening a bit smaller than the diameter of the egg. Of course, you'll also be needing an egg with its shell removed, a piece of paper, and a lighter, or you could use matches. So first, light up the paper. Let it burn for a while until the fire is lit. Then quickly place it inside the glass bottle as quick as possible and place the egg on top, making sure the egg covers the mouth of the bottle.
Hi there! So, let's just explain what just happened a while ago.
So first, let's say that the Gay-Lussac's law is similar to the Charles law, except for the fact that this law was studied by Joseph Gay-Lussac. So let's explain what happened in the experiment. So initially, the pressure inside the bottle and the surrounding environment was the same. However, when the paper that was lit with fire was placed inside the bottle and then sealed with an egg, the fire slowly extinguished inside. So when the fire slowly extinguished inside, the temperature dropped, and so did the pressure inside the bottle. Did so. And then the pressure outside was greater than the inside of the bottle. So the pressure outside pushes the egg until it gets inside.
So let's get to the main point. This law states that temperature is directly proportional to pressure. So, yep, that's it. So, ayun, as the temperature increases, the pressure also increases and vice versa. But guys, I want to show you another experiment. An experiment about all the gases.
That would be a candle, some pieces of clay for the support, water, a lighter, and a glass bottle. First, mold the clay so that it can serve as a base for the candle. Afterwards, place it on the tray. Then pour water until it gets surrounded by it. Then, light up the candle. Afterwards, place the glass bottle over it and watch what happens to the water.
Oh! Isn't it amazing? So basically, the combined gas law is the combination of all gas laws. To be more specific, it is the combination of Charles, Boyle's, and Gay-Lussac's law. Here, pressure, temperature, and volume are combined together.
Professor, I need to hurry for my class. I'm so sorry, but thank you for teaching me these concepts.
Okay, no problem. You may go now.
Thank you.
Bye.
Take care.
So, oh my god, the time flies so fast. I think we need to go to the main lab now.
Yes, Professor.
Let's go. That was tiring, but we made it. And are you guys still doing okay? Well, what a great scientific adventure we had. I hope you had a good time today, and don't forget to tune in to our...
He knows a lot about chemistry. Professor Ralph explains.